In this lab, I will demonstrate the end-to-end retrieval augmented generation pipeline, starting with chunking of text, indexing it in OpenSearch Vector Store, followed by a hybrid search of vectors, which includes vector similarity search and keyword-based search. Finally, I will demonstrate how you can retrieve the context dynamically by matching it with user's query and then use it to generate an output using a large language model. Hybrid search combines vector similarity search and BM25 based keyword search to improve retrieval quality. I will demonstrate the built-in hybrid search feature in OpenSearch, and I will also show you how you can implement an alternate approach of reciprocal rank fusion, which combines the results from vector search result and BM25 search results. If you have seen my other lab on comparing chunking strategies, you will notice that first few cells in this lab are same as the other lab. You can listen in 2x speed or fast forward to the point where we review the sample document for this lab. If you don't mind repetition or if you haven't seen the other lab, I recommend that you listen to the full explanation. In preparation of lab, I have created an open search domain, and inside the domain you will find the endpoint that we will use to make a connection. I have used AWS Secrets Manager for storing the OpenSearch credentials. I have created the secret that I will access from my code. And I have provided the credentials of my notebook, permissions to make API calls to Bedrock and Secrets Manager. As a first step, we will install some libraries. We need Boto 3 for interacting with AWS services, and we need OpenSearch Python libraries for vector indexing and retrieval. TQDM is to show progress bar. Let's import the libraries and classes that we need. In this cell, I have defined two functions that will help us extract password for OpenSearch from AWS Secrets Manager. In the first function getSecret, I have created a client for AWS Secrets Manager using Boto 3, and then I'm invoking API getSecretValue by passing in a secret ID. Secrets can be of type string or base 64, and depending upon whichever secret we have, we will extract it from the response and return it as a JSON object. Every secret is a dictionary of key value pairs. In this function, we are extracting the value of the key password from the secret. In this cell, I'm configuring the parameters that are required for making a connection with OpenSearch service. I'm setting the host name for the OpenSearch domain that I created, the username, and the password that we are extracting from AWS Secrets Manager. In this cell, we are creating a client for Bedrock runtime using Boto 3. We will use this client for invoking the embedding model for generating vector embeddings for text. We will also use this client for invoking a large language model when we generate an output for a user's query. Then I'm specifying the embedding model for this lab, which is Titan embedding model. It creates embeddings of 1536 dimension each. In this cell, I'm creating an OpenSearch connection by passing in the host name, the credentials, and by specifying some security parameters here. Notice the name of the client, it's called client, and we will access it throughout our lab for interacting with OpenSearch service. In this cell, I'm creating a helper function to embed a text using the embedding model that we selected. So here I'm using the Bedrock client to invoke the embedding model and passing in the text for which we want to create embedding. The response body contains the embedding. In this cell, we are defining a document that we will create smaller chunks of. We will create vector embeddings for each of these chunks and then store and index in OpenSearch. We will use these chunks to contrast between vector similarity search and BM25 keyword search and also hybrid search. Let us get familiar with this text as this is our search space. AgriNova is an AI-powered precision agriculture platform designed for large-scale vineyards and orchards. The system combines IoT sensors, satellite imagery, and machine learning models to optimize irrigation, fertilizer usage, and crop health monitoring. So this is the summary of AgriNova. The platform collects soil moisture readings every 15 minutes using distributed edge devices called hydronodes. These devices transmit telemetry through low power LoRaWAN network to a centralized analytical cluster. AgriNova includes a drought prediction engine trained on weather forecasts, evapotranspiration rates, and historical irrigation data. The forecasting service can predict water stress condition up to 10 days in advance. So this talks about reading the soil moisture and this talks about drought prediction engine. And then it reads farm operator use a feature called Smart Drip to automate irrigation scheduling. Smart Drip dynamically adjusts watering duration based on humidity, temperature, soil conductivity, and vine growth stage. A separate disease detection module analyzes multispectral drone imagery to identify early signs of powdery mildew, leaf rust, and nutrient deficiencies. A computer vision pipeline uses a light CNN model optimized for edge inference. For chunking this document, we are using the recursive chunking strategy, which basically preserves natural document structure by splitting this document on larger boundaries such as sections, subsections, and if they don't fit our chunk size, then we split them further into smaller boundaries such as paragraphs and then sentences. We do this by maintaining a list of separators that are prioritized. So we first start with the separators that are top of the list to split the document at larger boundaries. And then if the chunk does not fit in the maximum size limit, then we go to the next separator and so on. So that's the technique that we follow to create our chunks. And a benefit of recursive chunking is that it is easy to implement, very scalable. If you have the right size of your chunk, which is 120 characters here, you can minimize splitting of your chunks mid sentences or mid ideas. So let's chunk our document using this technique. And these are the chunks that have been created. Each row is a separate chunk. So as you can see, some sentences are fully contained in a chunk if they are less than 120 characters. However, some of them that are larger than 120 characters, which is the maximum size of our chunk, then they are split into two. I'll keep it like this to keep it close to how a real world system would be. The next step is to create our OpenSearch index for indexing these chunks. And the index is created by specifying the type of the index. So we have KNN equal to true, which basically means we are going to use approximate nearest neighbor algorithm for searching these chunks at the time of retrieval. We're also specifying the document structure, which contains text, which is the plain text of the chunk, the embedding, which is the embedding of that chunk, and some metadata, which in this case is chunk type. This cell basically looks if the index exists, it deletes it, and then recreates it. In this next cell, we are indexing the chunks using the index we just created. So here we have this method called index underscore chunks that takes in a list of chunks. It iterates over each chunk. The first thing it does is to create an embedding for the chunk using the helper method that we created. And then it creates the structure of the document that we will index. The structure has chunk in plain text, the embedding that we created for this text, and the metadata, which is chunk type. And then we index it in the index that we created. So let us index our chunks. In this cell, we are creating three methods for doing a similarity search of query with data that we have indexed in the open search. So the first method is vector similarity search, which basically creates a vector embedding of the query text and compares it semantically with the vectors that we have indexed in OpenSearch. It does it by specifying the query type to be KNN and then passing in the query vector that we have to search. It also specifies a parameter k, which basically specifies the number of nearest neighbor vector candidates that are retrieved internally when we search our query vector against indexed vectors. We also have this parameter size, which is set to k, and this specifies the number of final results that are returned to the end user. In this case, we have specified both values as k, but we could have had different values for each of these. The second method that we are defining is BM25 search. And in this case, we are again specifying k, but then the type of the query is match, which basically matches this query with plain text in the document. It doesn't match it with the embedding, it matches it with the plain text. Therefore, we are not creating an embedding here. We are simply passing the plain text query, which will be matched against the plain text saved in the document of our indexed data. And third method that we have created is the hybrid search, which basically combines both the approaches. You will see that we have the KNN node here, and we also have the match text node here. So this is the inbuilt hybrid search feature in OpenSearch. And in this cell, we are testing the three techniques by passing in this query, dry soil conditions, LoRaWAN. So basically, we are interested in finding all vector embeddings that are semantically similar to dry soil conditions. And we also want text that specifically talks about LoRaWAN. We're using the three search methods and printing the results from each of the methods. And the results we got for vector search are the platform collects soil moisture readings every 15 minutes using distributed edge devices called hydronodes. AgriNova includes drought prediction engine trained on weather forecasts, evapotranspiration rates, and historical. And the third result is the system combines IoT sensors, satellite imagery, and machine learning models to optimize irrigation fertilizer. So as you can see, dry soil condition is similar to measuring soil moisture, drought predictions, and optimizing irrigation. These are semantically related to the concept, although we do not have the exact words. And that's the beauty of vector similarity search. However, I do not see any LoRaWAN result in vector results. In the BM25 results, I do see LoRaWAN show up as the result number 2. You can see the first chunk here is similar in both lists, whereas the second one is different and this has LoRaWAN. So ideally, we want a combination of these two. I want this one along with some of these. The hybrid result here returns the first three results same as keyword search, and then it has two more which match the vector search results. Actually, fourth one is different. Fifth one matches the vector search result. And this is very typical because BM25 can assign very strong scores based on exact keyword matches. So even in hybrid search, oftentimes you will see that BM25 results are shown on the top. So here we saw the hybrid search using the built-in features of OpenSearch. What if you want more control on how these results are prioritized? If you want that, you can use reciprocal rank fusion. Reciprocal rank fusion is a ranking technique which is used in hybrid search to combine results from multiple retrieval methods. In our case, it is keyword search and vector similarity search. And in this case, instead of combining the raw relevance scores, which can vary in terms of scale on which they were computed, RRF works with document ranks, which makes it immune to different ranking scales of different search methods. The implementation steps are that we first run the two searches, that is BM25 and vector similarity search, independently using the same query string. And then we merge the returned results into a single list of documents or chunks that we rank using this formula here. So basically, this formula is to calculate a reciprocal rank fusion score for every document that is in the combined list. It takes into account documents' rank in both the lists. So basically, we take the rank of the document in the first list, add it to a constant k and inverse it, and then we take the document's rank in the second list, add it to the constant k and inverse it, and then we add these two together to create the final score. The role of the constant k is that it helps us to prevent top ranking documents from dominating too aggressively, while still rewarding documents that are high in the ranks and appear in both lists. So basically, we can reward agreement in both lists rather than a document appearing only in one list very high. Using RRF, we can customize the ranking by setting different values of K. A typical value of 60 is what is used to reward documents that appear high enough and are on both lists rather than just one. Let us see this using an example. Here you see four documents with their respective ranks in BM25 and vector similarity search. You see that document A is the top ranker in BM25, but it appears at rank 50 in vector similarity search, whereas document D is the top ranker for vector similarity search, but it appears at rank 20 in BM25 results. Document B and document C are on both lists and in reasonably high ranks. For example, document B is at rank 2 in BM25 and rank 10 in vector similarity search, whereas document C is at rank 3 and rank 5 in the two lists. So let's see what happens when we apply the value of K as 1. In this case, K is 1 means it has negligible effect. The rank has its importance. With K as 1, the high scorers are prioritized. As you see, document D and document A are prioritized over document B and document C because they are top of the list and their score are higher. Whereas if you make K as 100, the rank itself becomes less important because 100 is a big number. So document B and document C get prioritized, which are appearing high enough on both lists. In many real world systems, a value of 60 gives us very good results. So in our implementation code, after calling both the searches independently, we are merging the results and ranking the documents in the merged list using this method add scores. One thing to note here is that I've shown you a custom implementation of reciprocal rank fusion purely to build intuition into this concept and also to show you how you can tune parameter k to get optimal re-ranking for your use case. In OpenSearch, there is an inbuilt support for reciprocal rank fusion. You can create a pipeline and then create a score ranker processor in your pipeline to do reciprocal rank fusion if you're using OpenSearch. So let's run the query dry soil conditions LoRaWAN using the RRF fusion function that we created above. And as you can see, we have results that have been merged from each of the lists. We have the top scorer, which is on both the lists, and this one was the keyword search result, and this one was the top result in the vector similarity search. And in this last cell, we will see how we can dynamically retrieve context that is similar to user's query, augment it with the user's query, and send it to large language model for answer generation. So we need a model which is Nova Lite for generating our answer. And in this method, generate answer, we are taking in the query and a list of retrieved chunks. We are creating context text by augmenting all the contexts in this list. And then we are replacing context and query in this prompt template. Then we are using the Bedrock client to call the Converse API by passing in the prompt and some inference parameters. We're basically saying return at the most 300 tokens in the result. And we are setting the two parameters, temperature and top P, which basically determine the creativity or dynamic nature of the response. And as a last step, let us run the retrieval flow. We will first match our query with its matching context by calling the reciprocal rank fusion function that we created above. And then we will pass this context along with the query to generate answer function that calls the large language model. And our query is, why do we use smart drip? So the answer is, we use smart drip to automate irrigation scheduling by dynamically adjusting water duration based on humidity, temperature, soil conductivity, and vine growth. And if you see, the context that we sent was farm operators use feature called smart drip to automate irrigation scheduling, and smart drip dynamically adjusts watering duration based on humidity, temperature, soil conductivity, and vine growth. So I think it used these two to generate its answer. So this winds up our lab where we saw the end-to-end ingestion flow and retrieval flow for a retrieval augmented generation system. We started by chunking our text using recursive chunking strategy. We created an index in the OpenSearch vector store for k nearest neighbor search. After that, we indexed our chunks and implemented hybrid search using reciprocal rank fusion. And then we saw the retrieval flow where we matched our query with the context using the vector store and then passed it to the large language model for answer generation.